Well, welcome everyone to the WERA 103 presentation today. We're pleased to have Dr. Amber Moore presenting her latest information on soil pH testing, including the buffer pH method of determining the lime requirements of soils. Briefly, let me introduce Dr. Moore. Dr. Moore received her master's and PhD degrees from North Carolina State University. She then spent a year or two working with the U.S. Department of Agriculture in a postdoc position. After that, she joined the University of Idaho, where she was on the faculty there for about 10 years as a professor. And then most recently, she moved to Oregon State University in 2017. Amber's current responsibilities are for applied research, developing nutrient and lime recommendations for important crops in Oregon. So she has an active research program and an education program to help farmers in Oregon both manage their nutrients more effectively and to increase their production and do this in a sustainably viable manner. So we're pleased to have Dr. Moore with us today. This is a topic that she frequently gets asked questions about in terms of soil pH and what to do about remediating soils that may become too acidic. So glad to have you with us, Dr. Moore. I'm going to turn the presentation over to you and let you go ahead and get started.
Okay, thanks, Rob.
Great, we can see that fine.
Okay, great. Let's see. Okay, well, thank you for that introduction, Rob. Yeah, today I wanted to talk a little bit about soil pH and buffer pH. Soil acidity is pretty much permanently a hot topic here in Western Oregon because lime is quite a bit more expensive and harder to come by in this region than it is in other parts of the U.S. So when people are applying lime to fields, they want to feel really confident that they are putting the exact amount that is needed because they don't have the opportunity to apply in a more leisurely manner due to expense issues. So today I'm going to talk about soil pH, go through sort of the basics to help a more lay audience sort of understand what soil pH is and how it's tested. They're going to go into buffer pH, explain the chemistry there and some things we know about that and how it's used to determine lime requirement. I'm going to go through a few of the alternatives to the S&P buffer pH that we've been using for at least 50, 60 years here in the U.S. and discuss some research opportunities that might be coming from some of these alternatives. And finally, we'll have some recommendations for growers and producers as to what they can do now. So let's get started with the basics. So soil pH. Soil pH is simply the concentration of hydrogen ions in a soil solution. So it is a direct indication of soil acidity and soil alkalinity in the sense that as you have a larger proportion of hydrogen ions, that means your soil pH goes down and you have more acidic properties in that soil. Well, that's great, but who cares? This is a very technical, measurement, a lot of chemistry. Why does it matter from a grower standpoint? Well, growers really care about this, and there are some reasons for that, and that's because acidic soil conditions can cause a wide variety of soil fertility issues, including but not limited to things like manganese toxicity. That's very prevalent here in Western Oregon. Aluminum toxicity is the one you'll hear probably the most about when it comes to soil acidity issues. Phosphorus deficiency can be quite severe, and other deficiencies, including calcium deficiency and even molybdenum deficiency, can be an issue on various soils. Great, so how is soil pH tested in a lab setting? And it is, in a sense, one of the easiest, one of the more simple procedures that is done in a soil testing lab. And so the soil is mixed with a distilled water or a salt solution, and this will be hydrogen ions that are in the soil to float around in the solution. A hydrogen ion electrode is placed in solution, and this provides an immediate measurement of the solution pH. So the electrode is placed in the supernatant, which is the liquid portion of the soil solution. And the reason why I'm getting this detailed is because this actually matters. If you have somebody who's like new in the lab and they are putting the electrode lower into the soil mush or soil slurry at the bottom of the cup, this can actually change what that soil pH value is. So the water 1 to 2 method is the standard method that we use here at Oregon State University in our extension publications. And 1 to 2, all that means is that you have 10 grams of soil mixed with 20 milliliters of water. When this is done, the soil and the water is mixed, set aside for approximately 15 to 30 minutes, and then the electrode is placed in the liquid portion, and then a value is received. The water 1-to-1 method, which is even more common throughout the U.S., is the same thing, except use a 1-to-1 soil-water mixture. And it should be noted that the soil pH value will be slightly lower than the 1 to 2 method because the hydrogen ions are more concentrated. Because this is a more concentrated solution, you have 1 part soil, 1 part water, instead of 1 part soil, 2 parts water. And then there's a calcium chloride method, and instead of using water, they use 0.10 molar calcium chloride. And the intention here is to reduce the seasonal salt effect, but it should be noted that this will produce soil pH values that range from 0.3 to 0.5 units lower than the water method described above. And I want to mention all these caveats because a lot of people will, show me a soil pH from one lab and then from a different lab and say these are slightly different. And odds are there's slight differences between how they're doing their soil pH analysis. And so this is why I encourage people to kind of take that soil pH value with a grain of salt a little bit, that these things can cause it to vary slightly. So these are values that come from the came from the 2017 North American Proficiency Testing results. And so what happens is they have these anonymous soils. So in this case, it's soil 101, soil 102, and soil 103. And the soil testing labs, they don't know the properties of these soils, but they do a test and they see what ranges what test ranges they fall within, and to see if they match with all the other soil testing labs throughout the U.S. And this helps the lab kind of gauge where they fall and make sure that their testing results are in line with the other tests or with the other labs in the U.S. So here, this is the 1 to 2 test. So these 3 different soils have 3 different pHs, which is a perfectly normal thing that we see. It's just soil pH naturally changes. So the blue bar is the 1 to 2 test, and you can see the orange bar is the 1 to 1 test. And you can see that there is a slight decrease in that soil pH value. Is that enough to change management practices? Probably not in most cases, but it's still noteworthy. Now this includes the calcium chloride as well. This is the gray bar, and you can see it's actually quite a bit lower. And so again, if you're working with a new lab and you notice that your soil pH values are coming a lot lower than you thought that they should, you could always ask what kind of soil pH test they're using, and if they're using calcium chloride test, and that could explain that difference. All right, so now let's talk about the buffer test. So the buffers that are used to estimate lime requirement in soils, they contain weak acids and weak bases. And these acids and bases will react with the basic and acidic compounds that are in the soil solution that influence your soil acidity or soil alkalinity levels. So the typical starting pH value for a buffer test solution is 7.5. So you're starting with 7.5 in this solution. And after that, you add your soil. The buffer pH value will go down as the acidic compounds in your soil, the hydrogen and aluminum, will react with the basic compounds in the buffer. So that's why your buffer pH will start to go down and produce an acidic value. It's because it's reacting with these basic compounds in the buffer, and so it's taking these basic compounds out of solution and making it more acidic. It also goes the other way, where the buffer pH will also go up as the basic compounds, which are calcium, magnesium, and potassium, for example, in the soil will react with the acidic compounds in the buffer. So this is thought to be, or has been determined to be, a lot more reliable than just using pH for estimating lime requirements. You know, in the slides I showed you, pH can change very quickly because of you know, different conditions in the lab, or different water that's being used, or maybe even temperature and things that we didn't mention. Also, the buffer pH, it measures the actual amount of acidic compounds that need to be neutralized with lime. So it's not just measuring the proportion of hydrogen to hydroxyls in the soil solution. It's actually looking at the amount of hydrogen ions, and also aluminum and other acidic compounds that are in the soil, and also taking into account the calcium, magnesium, potassium, and other compounds. So it's a more literal estimate of how much lime is needed. And results are not as easily swayed by external factors in the lab as a soil pH test. So let's talk about the S&P buffer method specifically. So this is currently the basis for lime requirement estimates used in Oregon and many other states throughout the United States, or other states in the US. The buffer pH values were calibrated to the lime requirement determined from a soil lime incubation study conducted on 14 Ohio soils, and this work was done back in the 1960s. So this was done quite a while ago, and we've been sticking to this test to this buffer method for a very long time. In the method, they do say that the ideal soil pH is 5.8, is less than 5.8, and organic matter less than 10%. So acidic soils are what they're really targeting, and makes sense because these are the soils that need the most amount of lime. And it's designed for soils with a high lime requirement and appreciable quantities of exchangeable aluminum. So they're very much targeting the soils that would really benefit from a lime application. So this slide just shows you one of many, many examples of a S&P table where they show you the S&P value, and then they link it to the estimated amount of lime that is needed to get your soil up to a certain pH. And this was determined again from those lime incubation studies that were done on those Ohio soils back in the 1960s. So how does the buffer pH value compare to the soil pH value? I get asked this a lot when people say, you know, my buffer pH value, I feel like it's, you know, too different or too similar to my soil pH value, and people get concerned about that. So I wanted to show what the S&P buffer value looks like when you compare it to the soil pH. And one thing I want you to notice is it's quite a bit larger, and it varies. Like with the 101, you have 0.5, 0.6 units difference, while with the 102 it's closer to 0.4. And this just has to do with the fact that maybe one's a sand versus a clay, or one maybe has more aluminum, maybe one has more calcium from an older lime application. And so they're not supposed to be close to soil pH. They're kind of an independent thing. Again, it's just a buffer that changes in its value as you add more soil and as it reacts to it. So it's a completely different mode of action, and it's not supposed to be highly correlated to soil pH. All right, so I now want to talk about the introduction of the Socorro buffer. So previously, most labs in the Pacific Northwest and throughout the United States use the S&P buffer for buffer pH and lime requirement estimates. And this has been how things have been for many, many decades. But just recently, people started using this newer Socorro buffer. And to give you an example of kind of how this shift is going, the NAPT Soil Certification Program in 2017 had 29 of the participating labs were using the traditional S&P buffer. However, 31 participating labs were actually using the Socorro buffer. And that is showing that there is a pretty significant shift going on in these commercial labs toward the Socorro buffer. So why are labs switching from the S&P to the Socorro buffer? So the S&P procedure uses p-nitrophenol and potassium chromate chemicals. And these are hazardous, and they're quite difficult to dispose. And so there's been interest in quite a long time by soil testing labs to change or to do something that is much. So Frank Socorro developed the Socorro buffer, and it was designed to mimic the S&P test. And so in this method, he replaced the p-nitrophenol and potassium chromate with 2-morpholino ethane sulfonic and acid monohydrate and imidazole. I'm sorry, it's probably the first time I've said that, but it's not easier to say than the S&P method. But anyway, those are the chemicals that they replaced it with. It is much less toxic than the original S&P method, and that was the whole point. And sometimes it may be referred to as the modified S&P as opposed to the Socorro method. So lab testings in other regions have shown a strong correlation between the Socorro and the S&P buffer pH values. And here's an example of that. So this is a comparison done with 1,252 soil samples from Iowa that were submitted by farmers. And you can see, so the red dashed line is a one-to-one relationship. And we're looking at a comparison between S&P buffer pH and Socorro buffer pH. And in the world of soil testing, this is actually a halfway decent correlation. And is this good enough for the consumers? That's really up to the consumers, but this is what they found. And so it's these kind of relationships that the soil testing labs are using as justification to switch over from the S&P over to the Socorro. When you look at the NAPT proficiency results, when they did a Socorro test, and that is sort of the royal blue or darker blue bar, if you compare that to the S&P, you can see that the values are actually quite similar. The Socorro buffers look like they are just slightly higher. In this case, it would not be high enough to change management practices. And in some cases, like in 102, that difference would almost be considered negligible. So what I do want to mention here, though, is that there are indications in other regions that the Socorro test may be inconsistent, and it might be somewhat higher than what we're showing in this table or in this graph. And so what I want to emphasize is the importance of doing what they did in Iowa. Sorry, let's let me go the other direction. What they did here in Iowa for your own region, so that you can be confident that you're seeing these sort of relationships for your own soils. In Western Oregon, we're seeing a trend where the Socorro buffer seems to be predicting sometimes quite a bit less lime needed than the S&P, and it's and we're trying to find out if there's a validity to these observations or not. So question is, are there other methods that we should be considering for estimating lime requirements? Recently, in the Palouse region, a graduate student, Carol McFarland, worked with Dave Huggins with ARS, and she was with Washington State University, and they worked with 10 different Palouse soils, and these are less soils from that region. It's a dry land wheat production region, and they played with these different buffers and compared them to a lime incubation study. And they actually found that the modified Malick buffer had was the best predictor of lime requirement in this test compared to some of the more traditional ones like Woodruff, ones that you don't hear about as much anymore, but Woodruff and Adams. Socorro did okay, but not nearly as well as the modified Malick. And then S&P was actually did not have a great correlation to how much lime was actually needed. So some of the questions that I had after seeing this was, would the modified Malick buffer work for other acidic soils in other regions, or are these findings limited to just the Palouse region? If it would work for other acidic soils, then do we need to start working with soil testing labs to change their buffers and work with universities to start changing their lime recommendations if necessary? Another example, this comes from University of Wisconsin by Peters and Lebowski, and they actually found that the best predictor for lime requirement was a combination of pH and buffer pH. And I asked Carrie Lebowski about this personally, and she said that this, they looked at a lot of different things, and this is what it was this equation that had the highest correlation. to lime requirement, and so that's why they were using it. I should also mention that the buffer pH in this case was actually the Socorro test. Finally, this also came out of the study that McFarland and Huggins worked on a few years ago, and they actually played with looking at pre-plant soil test values. So they kind of threw out this idea of the buffer test and said, what if we just look at some of these parameters in the soil? And so they actually looked at electrical conductivity, soil organic matter, base saturation, and potassium chloride extractable aluminum. And they got their highest R squared of 0.98 for lime requirement connection to this these 4 different variables in an equation. And so that I'm very interested in this concept of not using buffer tests at all, and actually using several different pre-plant soil tests to understand and potentially be a more accurate predictor of lime requirement. Again, this was done on only 10 polluted soils, so this is definitely not ready for public consumption or to be adopted by soil testing labs, but it's definitely worth a discussion. You can see here that the soils that they used were very similar in soil texture and organic matter, and so there's not, you were not picking up much variability here. However, they did do a pretty good job at ranging their soluble aluminum from 8 to 139, which I thought was well done. It really indicates this difference in lime requirement, and they're really picking up on that. So what are the research opportunities here? So these are some of my own interests, but I think that there's other scientists throughout the U.S. who would be interested in this as well. And one is to determine if these McFarland findings from the pollutes extend to a broader range of soil types. In other words, should we be considering this modified Malick buffer instead of the S&P or Socorro, or maybe a different buffer to estimate lime requirement? Or should we consider ditching the buffer test altogether for a multivariate approach? That is, definitely would be a major shift in how things are done, and so that would probably take a minimum of 5 to 10 years of research before that kind of change would be made, and it's still not. We haven't determined if that would even be an appropriate move. So what should growers do in the meantime, since we are in a bit of flux here? So I always recommend finding ways to reduce variability on their end, and this could mean things like making sure that you're consistently sampling from the same soil depth, the same time of year, sampling the field the same way, whether it's a composite, a map zone, or a grid sampling technique, and use the same soil testing lab. If any of these alter, it's not a big deal, but then you are starting to compare apples and oranges. If you're showing me a soil depth of 0 to 3 and then comparing it to a 0 to 6, and you're telling me that they're different, you might have something different going on at a 3 to 6 inch layer, and it's sort of changing your results. Also request the same analyses. So if they are doing a different type of pH test or buffer pH test, that can also cause your numbers to change. If any of these variables change, then just restart your clock on your soil pH and your buffer pH tracking over time. All right, so what else can growers do? All in all, I still recommend putting more stock in your buffer pH than your regular pH when it comes to estimating how much lime you need for your fields. Again, there are just too many factors that influence the soil pH testing, as we showed earlier in this presentation, which is why soil pH alone is not used for lime requirement estimates. In some parts of the U.S., Socorro buffer pH method has produced consistent results in line with the lime requirement. However, in Oregon and other states where Socorro has not been validated, my recommendation is to continue to use the S&P buffer. Finally, ask your lab what tests are used for pH and buffer pH. Here in Oregon, some of the labs changed from S&P to Socorro within the last 4 years, and people noticed that they were getting different values, but they did not realize that this change had occurred. So it might be worth, if you are seeing differences in your buffer pH value and you don't understand why, it may be worth giving your lab a call. and asking if they've changed recently. Another thing you can do is you can check on your exchangeable calcium levels over the years. And the idea here is that this will give you a more constant indication of your hydrogen and calcium exchanges that are occurring in the soil compared to pH or even buffer pH testing. So pH can bounce around, because time of year and other things that we showed. And so this may give you some peace of mind as to like where your soil acidity levels really are. And then finally, listen to your gut. Lime is, especially in our region, can be quite expensive. And so, if you feel like something is off on the soil test, you listen to your experience and make a good, an appropriate decision for how much lime is needed. We are doing the best we can with the chemistries that we have, but lime is estimating exactly how much lime is needed to bring a pH up to a specific value is not a simple procedure, and it can be complicated, and will always be imperfect in my opinion. So it's one of those things that you have to also make sure that you take your experience into account. I'd like to acknowledge a lot of people helped me with this presentation. I put this together after I'd only been here at Oregon State for a few months, and it came to light that this was a question a lot of people had, so I had to give myself a pretty quick crash course in buffer pH and soil pH, and so these colleagues helped catch me up quite quickly, and I really appreciate their support. And with that, I'll sign off, but I really thank you for taking the time to listen to this presentation today. I hope it maybe opened your eyes to different things that are going on. This is my contact information if you'd like to get a hold of me. And that's all I have for today. Thank you.
Well, thank you, Dr. Moore. We encourage people to contact you for additional questions. This is a complicated subject and one where the science is still evolving. So really appreciate your willingness to help educate us on what the state of the knowledge is and how to proceed when we have questions related to soil acidity. So thank you, and we encourage people to go to our library on our YouTube channel and regularly get an update on some of the latest soil fertility information that's being developed in the Western United States. So thank you, and hope you enjoy the other videos. Okay, bye-bye.